So, today we're going to talk about something that's way more than just a math concept. We're unlocking a tool that lets us see the world in motion, a way to capture the very essence of change with just a single number. We're talking, of course, about the derivative.
I mean, just think about it for a second. Everything is always moving, always changing. You know, from planets hurtling through space, to the price of your morning coffee, to the car you're driving down the highway. Nothing ever really stands still.
And that's really the tricky part, isn't it? How fast is that car going right now? Not over the last mile, but right this second. How quickly is the stock price changing at exactly 10:32 a.m.? Measuring change over an hour, that's easy, but measuring it in an instant, where, no time has actually passed, that's a real head scratcher.
And the answer, when it finally showed up, after centuries of people thinking about it, man, it was a game changer. The derivative gave us the mathematical language to talk about the rate of change at any specific moment, with perfect precision.
Okay, so how does this whole thing actually work? Well, to really get what a derivative is, we have to start with something we all get, the idea of an average.
So, an average rate of change is super straightforward. Let's say you drive 120 miles and it takes you 2 hours. Your average speed? 60 miles an hour. Total distance divided by total time. Easy. Simple enough, right?
But of course, you know that on that trip, you weren't glued to 60 miles an hour the whole time. You were stopped at lights, you were speeding up to pass someone. Your average speed tells the story of the whole trip. Your speedometer, though, that tells you the story of right now. And that right there is the huge difference between an average rate and an instantaneous one.
So, the big question is, how do we get there mathematically? How do we calculate the speed at one specific point in time when we don't have a start and an end to average out?
Okay, this is the magic trick, right here. This is the big idea in calculus. We start by calculating an average speed, but over a super tiny interval, like 1 second. Then we start squeezing that interval, 1/10 of a second, a millionth. As that little chunk of time gets closer and closer and closer to zero, the average speed starts to lock onto one single number. That number is the instantaneous rate of change.
And that, my friends, is the derivative. It's the mathematical tool we use to find the rate of change, not over the whole journey, but for that one precise moment of right now.
All right, so let's take this idea out for a spin in the real world, where we experience it all the time, in motion. So think of it like this. You've got a formula for where something is at any time. Take the derivative of that and boom, you've got its velocity. That's how fast its position is changing. Now, what if you take the derivative of the velocity? Well, you get acceleration, how fast its velocity is changing. It's just this beautiful chain of derivatives, one after another. Let's look at a ball dropped from 64 feet high. So it takes 2 seconds to hit the ground. Its average velocity during that fall is 32 feet per second downwards. But here's where the derivative shows us something way more dramatic. At the exact instant it hits the ground, its velocity is a whopping 64 feet per second. The average totally hides the story of that final, intense moment.
But the derivative can do even cooler, more subtle stuff. Imagine a tiny particle just moving along a line. How could we possibly know if, at one specific instant, it's speeding up or slowing down?
Well, by looking at the derivatives, we can be detectives here. At this one moment in time, its velocity is negative, which just means it's moving to the left. But its acceleration is positive. It's like a rocket trying to push it back to the right. So you've got these two forces fighting each other, one pulling left, one pushing right. That means, at that exact instant, the particle has to be slowing down. And what's so cool is that this idea isn't just for physics nerds. It lets us do some amazing things like peek into the future by looking at stuff like population growth. So here's the really powerful idea. If we know how many people live in a city right now, and we know its derivative, that is, the rate it's growing right now, we can actually make a really solid guess at what the population is going to be next year.
Okay, let's imagine a city, right? It's got 10,000 people. We use the derivative to figure out that its current growth rate is about 4,000 people per year. So with that little snapshot of its growth, we can project forward. To guess the population in 2 years, we basically just add 2 years of that current growth rate onto the population we already have.
And what do we get? A prediction of around 18,000 people.
I mean, think about that. That's so powerful. We just used a snapshot of today's rate of change to forecast what's going to happen tomorrow. It's like a little crystal ball, powered by math.
All right, for a last stop, let's bring this whole idea into the world of business and economics,
where knowing your rate of change is absolutely key to making good decisions.
So, in economics, you'll hear the word marginal thrown around a lot. Marginal revenue, marginal cost. Really, it's just a fancy word for the derivative. Marginal revenue answers a simple but super important question. How much more money are you going to make if you sell just one more thing?
So picture this. You're running a BBQ joint, and you've already sold 100 dinners tonight. You want to know what's the real impact of selling that very next plate, the 101st one. And this is where the derivative is just a fantastic shortcut. Instead of doing a bunch of complicated math, you just find the marginal revenue, the derivative, at 100 sales. It gives you an estimate of $3. And look how ridiculously close that is to the actual number, which is $2.97. It's a super fast, super accurate way to make decisions right when you need to.
So after all that, what have we seen? Well, it turns out this single mathematical idea, the derivative, isn't just a bunch of numbers on a page. It's like this universal language that describes how things change.
I mean, we've seen it describe a falling ball with perfect accuracy, predict how a city will grow, and help make crucial business decisions. It's the key to understanding change in physics, biology, economics, you name it.
So look, as you go about your day-to-day, just think about all the things changing around you. The temperature outside, the traffic on the road, maybe the balance in your bank account. Every single one has a derivative, a rate of change happening in this exact instant. The real question is, what's the one rate of change that matters most to you right now?